going to continue what we discussed last time, but I'll remind some of the definitions. We had the class VP, which is polynomials with polydegree and with polynomial size circuits. This corresponds to P/poly in the Boolean case. We had the class VNP, which is polynomial f, which can be written as sum of E1 to ET. We had the class VNP, which are polynomials that can be written as a Boolean sum over some other polynomial. This polynomial has the number of variables in this polynomial is polynomial in N, and it's a polynomial in VP. So this was VNP. And what we wanted to prove is that the permanent of a matrix which is equal to sum that the permanent of a matrix is that this polynomial is VNP-complete. And this means that for every polynomial, so completeness means that the permanent is in VNP. We saw this, and it means that it's VNP hard, which means that every polynomial f can be embedded into a permanent of a matrix M of f, and this has a poly n size. So this is what we wanted to prove. And to prove this, so is it okay by so far?
There's nothing about this embedding, like.
Yes. So yeah. So MF, every entry is either a variable or a field element in our field. And to prove this, we had 3 steps. The first one is to say that without loss of generality, this G from this has the first step was to say that this, without loss of generality, if we consider f in VP, then write it more formally. So if F has polysize circuit, then we saw that we can simulate circuits with the Boolean sum over formulas, which means that if every polynomial that has a polynomial size circuit can be written as a Boolean sum over a polynomial size formula. And this is the analog of the Cook-Levin theorem in this context. The second step was to say that the permanent is universal, which means that so the second statement that we didn't prove last time, which we'll prove today, is that if a polynomial has a formula of size S, it can be written as the permanent of a matrix with the same structure, and the side of this matrix is roughly S by S. And the third step, which we will also see today, is that the permanent allows Boolean sums. And what does this mean? This means that sum, so if M is S by S matrix and B is some element that appears S of B times in the matrix M, then exists M prime. No, we want to prove that every polynomial that has a polynomial size circuit.
So if G
Oh,
has
okay.
polynomial size,
Yes, so, yeah, okay. The both of the statements are the same because of the definition of VNP. So, yeah, okay. So this is equivalent to saying that it is in VNP.
no.
I think that this is correct.
No,
No, yeah, you're sorry. Yes, not that F in VNP. So this is what we proved, and this is enough for us.
don't you want to say that if F has polysize circuit, then F has polysize formula?
No, this is what I.
No, it's an open question. It's not an open before. But if you add this Boolean sum, then it becomes.
Oh,
But
Then you can reduce the circle of formula.
the G.
Where?
Yeah, it's
It's the
yeah,
G there.
it's local variable.
Yes. Yeah. Yeah. So, but what I tried to say, I'm not sure that I was clear, that this statement,
So it's not exactly a complete. Okay.
yeah, you can
Okay.
call it in many names. But maybe, so this statement implies that in the definition of VNP, we can assume that this has, this is with lossless generality, a polynomial size formula instead of a circuit, because we can put another Boolean sum here, and it doesn't really matter. Yeah, this is okay. So I didn't explain the third part. So the third part is special for the permanent, and it says that if we have a matrix of size S by S, and there is some specific element that appear in M, S of B times, so we have like B, 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 somewhere in the matrix, then there exists some other matrix, not much larger, of size S plus 7B, that the permanent of this matrix is the Boolean sum over the permanents of these matrices.
So we said last time, you might want to also mention that for any other element B prime, so S prime sub B prime equals S of B prime. So the number of
So
occurrences in M prime is the number.
for every B prime, not B, for yeah. It's yeah, it's maybe confusing, but
Nothing deteriorates in the occurrences of
yeah.
other variables.
So actually, this matrix will be a very, very simple matrix. It will be exactly the same as M, sort of, and there will be some other new places which are constants from the field. Okay, it will be a very simple matrix.
So B is a variable?
Yes. And this will work only when 2 has an inverse. We'll see why this is true. And we last time explained how these three things imply the completeness of the permanent. Maybe if we'll have time at the end, we'll explain it again. But it's not very complicated. Okay, so let's today we'll see steps 2 and 3. The first step we saw the last time. So we want to now argue that the permanent is universal. And this will also be true for the determinant. And I'll try to explain. So what do we want to do for every f? So this is what we want to prove. Of
Why just dimension S plus 1? Just this product is confusing, especially when you add or
okay. So how do we prove such a statement? Sort of the only way to do it is by induction. At least, yeah. Okay. So let's try to do it by induction, but in many cases, to prove something by induction, we need to require some stronger property that will make the induction work. And this property in this case will be that M of f has a very special structure. In all the lower left side, it is 0. Beneath the diagonal, it is all 1, and we don't care about what is written above the diagonal. Okay, so in fact, we will show that the structure of MF is this structure. Okay, so let's start. When the size is 1, then we just have either, so f is either xi or some element of the field. And we want MF to have this structure, so we will define M of f to be this matrix, and its permanent will be equal to f, because the permanent is...
Why don't you want the 0 to be below the diagonal to make it match your picture?
No, so every entry on the diagonal is something. Every entry...
Below the subdiagonal, one below the diagonal is all ones. The diagonal and up you don't require anything.
So yeah, this is like all of this here is a diagonal. This is the one entry below the diagonal. Okay. Now, if we have a formula where so let's do the simpler case. When the upper gate is a product gate, then here we have some two other formulas, and the size of these two formulas, S, is at most is equal to this, because we have S1 gates here, S1 gates here, and another gate here, S2 gates here. So we know by induction that there exists M of Fi of this form for every for both F1 and to F2. So in the product case, it's very simple, because we know that if we put here M of F1 and here M of F2, and here write zeros, then the determinant of this matrix is a product of the determinants. So
It's both.
permanent, sorry.
Yeah, everything will work for permanent.
Yes, I'm sorry. So permanent. Yes. So we know this, but here we do not continue the same structure, because here we are missing a 1. But if we write here a 1, we don't change anything in the value of the permanent. So we can write here a 1, and this equality still holds. So this is what we do if the upper gate is a product gate. And the last case, which is the most complicated one, is that we have some gate at the top. And here we will actually use the structure of M we kept. So what will we do? Again, we have M of Fi of the relevant structure. So we define M of F to be okay.
What do you mean by the upper?
So all of this matrix is M of F1, but it has this structure by induction. All of this matrix is M of F2, but it has this structure. And now we add one more row and one more column. These two matrices, these two matrices will be 0, and we add one here, here, and here, and here. And so we have to prove two things. First, that the permanent of this matrix is the sum of the permanents. And second, that this matrix has the needed structure. Well, this matrix does not have the needed structure, but if we swap these two rows, it will have the needed structure. And this does not affect the value of the permanent. So let's leave it in this form because it will be easier to see the other part. Okay. So we want to show to compute this. So we'll do a row by row expansion of the permanent. So we need to choose some position in the, so that's right.
Not row by row, just expansion by the first row.
Yes. So we need to choose some position in the first row that is non-zero, and then we take the corresponding minor out. So let's choose this position.
The one in the bottom left is not in the right position. Bottom left, left.
Yes. Yeah. So if we choose, we delete this minor. So we have the permanent is the sum of this. So the permanent of this matrix is the sum of these two permanents. We either choose this non-zero entry or this non-zero entry in the first row. Now, the permanent of this matrix, what is this matrix? This matrix is a...
Zero row, right?
No.
No, this matrix has 1 on this diagonal. So now, because we deleted the last row, this became the main diagonal of the matrix. So the permanent of this matrix is the permanent of M of F2. And the permanent of this matrix, well, it's exactly the same. If we change, like if we move this one to here, we'll get exactly the same structure as we get here.
We don't
I
move the
still
one.
think it still looks like there's a non-zero row right above the line.
Which line?
The
No, there is
middle.
one.
Here there is one. No, this is,
Okay.
yes. Okay. So the permanent, this is the permanent of M of F1, M of F2, plus the permanent of M of F1. Okay, so all the entries in the matrices are just field elements in the last step, in the first step in the induction. And all the other entries are just zeros and ones. It's a very sparse matrix. Almost all the entries are zero. And what else? Yeah, the same proof will actually work for the determinant as well. The only difference is that we sometimes need to take -1 to take care of the signs. But other than this, this also shows that the determinant is universal. Okay.
Can work for determinant with the same size, with the same dimension.
Yeah, exactly. Everything is the same proof even. You just sometimes, because of the determinant cares about position, right? Then you need the same sign, some of the ones to -1. There's nothing, the only property of permanent determinant used here is that, if you have a block matrix, then the permanent of a block matrix is the product of the permanent of this block.
This is
And
this.
Similarly for determinant, that's the only thing used here. And expansion, and that they have an expansion formula. It's the same for both.
Okay.
What if F has small circuit size? Can you say anything?
So yeah, it's a very good question. So here we heavily used the fact that it's formula because of this property. The two subtrees are disjoint, so the size is the correct size. And for circuits, I don't know of any such proof, like by induction. And sort of one reason for this is that this should not, we do not think that circuits can be simulated by the determinant, which if something will work for the permanent, it will like by this kind of thing, it will probably also work for the determinant. And we don't think that this should be possible. So the only thing that makes the permanent more strong is the third statement, which the permanent somehow allows to take Boolean sums, and this is good enough to take so we can assume that we have a formula if we also allow a Boolean sum. So the first step tells us that a circuit without loss of generality has a Boolean sum and the formula. The permanent can take care of this Boolean sum somehow, but I don't know of any way to do it without going through formulas.
If you allow quasi-polynomial size, then it's okay, right?
Yes.
Because circuits can be simulated by formula, not just quasi-polynomial size. So the permanent and determinant are sort of universal. Quasi-polynomial is universal also for arithmetic circuits.
Yes.
And Login.
Okay. And maybe another comment. So the first time I heard this specific proof is from Avi. I'm not sure where.
I don't think it's. I didn't see it written anywhere like this. There is some paper of Ken Reagan, which has some similar proof.
Yeah, and in Valiant, in his paper, proved the same statement, and he used the connection between the permanent of a matrix and cycle covers of graphs. And then maybe you have a bit more combinatorial understanding of what is going on. And we'll actually use this connection between cycle covers and permutations in the third step to give some intuitions about what is going on there. Okay, so we have that the permanent is universal, and now let's prove the third part.
I was going to say that this step with the matrices for determinant was the same bound written on this.
Which one? This is the Ken-Regan one or no?
It has multiple authors. I can find it easily.
So there was no similar. Yeah, it's yeah. I mean, that's
To translate Valiant's proof of cycle covers, is it doing the same operation to the matrices, or is it doing something different?
No, it's different somehow. Yes. Okay. So. Okay, the proof of this statement also has two parts in it. The first part is that I will write something and try to explain. The permanent allows coupling. So we'll show first that the permanent gives us some additional power, and then we will use this to conclude the proof. Okay, so let's start with this part. The permanent allows coupling. Okay, so what does it mean to allow coupling? We have some matrix N, and we choose two positions, P1, position 1, and position 2 in this matrix. And we'll choose them so they are not in the same row or in the same column. They're in different rows and columns. They look like this. Then we can write a matrix. So this is this matrix. We can take the matrix, write a matrix with adding 3 more rows and columns to the matrix. So here there are 3. So let's call this matrix M after coupling P1 and P2. So that here we write 0. All the matrix here is exactly the same as M except these two changes. Here. All of these entries are 0. And okay, what do we do here? So in all of these places, we write some field elements and the entries that were written here. So it's something like here you write x and 0 and 0, y 0, 0, 0, 0, 1, 1, 0, 0. And here this matrix is something like 1, minus 1, 1 half, 1, 1, minus 1 half, 1, 1, minus 1 half. Something like this. No, there is a specific matrix you want to write there. Okay, I don't remember it, so maybe I will write it for Pavel. This is minus 1. This is what you write. But okay, what is the property of this thing? The permanent of m prime is equal. So the permanent of the new matrix will be a sum of two sort of permanents. The first, so this is a sum of two permanents. The first one is a sum over all permutations that go through both the position P1 and P2. So I1 is J1 and I2 is J2.
So P1 is I1, J1.
Yes. And the other type of permutation is the permutations that do not go in both of them. Yeah, in any of them. So this is why I call this a coupling. This is why it's called a coupling. The permutations either go in both of them or in none of them. Okay, so the statement of what I wrote is clear. Okay, let's try to give some intuition about the choice, this choice, and what's going on here. One comment is we wrote 1/2 there, which means that 2 has an inverse. Okay, so here we used that the field is not of characteristic 2. Okay, I'll try to explain this transformation. So there is this correspondence between permutations and permutations of M and cycle covers of M as a graph. So every permutation can be written as its cycle structure. We see where 1 goes to, say it goes to 5, then we see where 5 goes to, it goes to 7. So at some point we close a cycle and then we start a new cycle. So we compose the permutations into cycles. And the permanent, so the permanent is the sum over all permutations. We can write it also as a sum over all cycle covers of M, where we think of M as a directed graph whose edges are labeled by the entries of M. So I don't want to make it too formal, but there is this correspondence. So how does this translate to this language? In this matrix, we have 2 specific edges that are labeled by X and Y and go from Y1 to J1 to J2. And we want to somehow add some vertices to this graph so that every cycle cover of the new graph that does not go on these 2 edges together or on none of them will cancel, like will contribute 0. Yes. So how do we do this? So we added 3 rows and columns. So this means that we add 3 we added 3 vertices, 1, 2, 3. This is I1. And J2. And now we add, erase this just to. We add these loops, and we add these edges. And we add these edges. We add this edge. So we add this structure inside the graph. And now we label the edges here according to the rule that is written here. So the edges from I1, so this is like the vertex 1, the vertex 2, and the vertex 3. And this is 1, 2, 3. And 1, 2, 3. So I1 to 1 is labeled by X. I2 is going to 3, and it's labeled by Y. Okay, and we can. So I want to just write it so that I'll give one example that will clarify why this. So let's see, from Y1 to itself is -1, from Y1 to 2 is 1, from Y1 to 3 is 1/2, from 2, this is 1, this is 1, from 2, yes, from 2 to 1 is 1, from 2 to 2 is 1, from 2 to 3 is -1/2, from 3 to 1 is 1, from 3 to 2 is 1, from 3 to itself is 1. Okay, so I just copied what is written here on the graph. And now we want to say that if we have a cycle cover of this new graph that don't go on these two edges together, or just ignore all of this structure, it will cancel itself.
It will never ignore this structure because it will pick maybe the self-loops of 1 and 2. So
Yes.
So you just want to say that if it goes through exactly one of the x edge or the y edge, then it will
We can just say,
contribute.
say, let's look at the ones that go through neither the top nor the bottom. Then you remove I1, J1, I2, J2 from this picture, and you say what's each one of those gets multiplied by the cycles covered for that subgraph. If it's going through.
But you don't remove both. You want those that use both to remain.
Well, yeah, so what I'm saying is that product should be 1.
One, right.
When
Good.
you take the sum of all the cycle
Yes,
covers of
yes.
that middle gadget,
That's
it
right.
should give you 1,
That's
so
right.
that they remain. You look at the ones that go through both,
Yeah, so
well, that's just x times y,
Yeah.
because you're using all the straight edges.
yeah, so
And then you look at the ones that go through just the top, that means you're
So-
counting those by negative a half.
so I'll try to explain, to give one example of what Russell is now saying. So let's see why. So we take a cycle cover and write all the cycle covers that go on this edge and on this edge, but do not take this edge. So we take one cycle cover that take, for example, x, does not take y, and went on this edge. Let's choose such cycle cover, for example. Then the two ways to get such cycles cover from this picture, one is to take this edge and this edge, and and no, this is not good. So we cannot do this. So one option is to take this edge, right? Then it becomes this edge and this edge. This is one option. And what is the other option?
To go straight to 2 and go down.
Yes. This is the other option, is to do this. Okay, so each cycle cover, we fix the cycle cover of the big graph. Each one of these that go through here and here can be written as two cycle covers of this part. So what is the weight of this cycle cover? It's the product of this and this, which is 1/2 times 1. So this is 1, and the weight of this is 1 and minus 1/2. So 1 times minus 1/2, which is 0. Okay, so the total contribution of such cycle covers is 0. Okay, and there are maybe 6 cases to consider to argue that all of this structure actually satisfies what we want.
Yeah, but you need to do both things, what Russell said also. So the bad ones cancel and the good
Yes.
ones give contribution of 1.
Yes. Okay. So I don't think it's enlightening to see all the other examples.
Yeah, what's sort of enlightening is that A, such a structure exists.
Yes.
And B, that it forces 2 to have an impact.
Yes.
So is it crucial that 2 be invertible?
Yeah, it's crucial for this reduction, and if
Ah.
it weren't, then the terminal could do it also.
in characteristic 2, the determinant and the permanent are the same polynomial. So this is
Sorry, when you say crucial, you know it's impossible.
Yeah,
Unless
I-
the
I-
determinant is the same determinant.
if it was possible,
Yeah.
then you could.
There's no.
I don't know. That's the only proof I know. That it's unlikely. I mean,
Unless
Yes.
it's
yeah, it's possible that the permanent is the same as the determinant, and in general, that it's reducible to determinant, and even that doesn't mean that there's a gadget. But
Amir just explains like the ultimate answer.
oh, this is what.
Because this is what
Yes. Okay. So I think it's a good time to have a break. Yeah, after that we'll use this coupling to complete what we wanted. These are calls, I'm not sure how to write it or pronounce it. Something like this, maybe 2 S's or 1. Here we'll put some specific graph, which I'll describe. It's called the rosette graph. And then we will couple these positions with this diagonal. So we'll couple this with this, this with this, this with this, and so on. And then, after doing this coupling, we will get, this is the same matrix. Here it is almost the same matrix. And here we added some 3 SB, it's 2 SB. To do the coupling, as we described in the first step. For every 2 positions, there are SB of them, we add 3 new vertices in the graph, or 3 more new rows. That's this. Okay, so we'll take this matrix, write this matrix. Here there are constants, 0, 1s. And here there are 0, 1s. Here there are some inverses of 2, and something like this.
Does the order of the coupling matter? Does it change anything?
No.
So it's the same matrix.
Yes. So the ordering of the coupling will change this matrix, perhaps. But it will be up to symmetries, so the same matrix. It's a big matrix. Okay, so I want to describe the rosette graph or matrix. The rosette graph will have 2s vertices. There will be, so let's choose, there will be 5 main vertices and some other 5 less main vertices. Here. We have this cycle. We have this cycle, and we have self loops everywhere. So this is, there are 2s vertices and there are some edges. How does it look like? So let's call these. So we write on this side these vertices, and here we write these vertices. So here we'll have, all of them have self loops, so we have the identity. The upper level also has a shift. So we add a shift. A shift means that position I here is connected to I plus 1 modulo S of B, S sub B. How are these connected to this? Let's say by the identity. And then these are connected to these by a shift. Okay, so we have this matrix. This matrix should describe this graph. And it's not so important what is written here. There are two important properties of this graph that we are going to use. The first property is for every subset let's call this one. I label the vertice, these edges. Okay. For every non-empty subset, there is a unique cycle cover. So that sigma of I is I plus 1 for every I in. Okay, what does this mean? For every non-empty subset of edges, such as we choose to be in our cycle cover, the only way to complete it to a cycle cover is unique. So let's say that we chose these two edges. Then we do not choose.
And if not,
Yes.
why not?
So we did not choose all of these edges. So this means that we must have chosen this edge, and this means that we must have chosen this, and so on. So if we chose these two edges, the only way to complete it is by choosing, yes, and these. No? Okay, so this is one property we are going to use. In the second property, there are exactly two with T being the empty set. And what are these two? One is this cycle cover.
Sorry, how is that with T being the empty set?
So we don't choose any. Sorry. You're right. I confused. So I'll make it 4. Yes. Thank you. So there are exactly two ways when this set is empty. Okay, it's maybe it's not so clear why do we want this, but I think it will be clear in a few minutes. So let's imagine that this is 5b. So maybe it's 5, not 7, what I wrote before. That this is 5b, and we already coupled these positions. So here we have, these positions are already coupled. And so in this part, we have the matrix M when b is equal to 1, when we substituted all the entries b to b1. And now what happens when we, so let's do two simple things. What is the permanent of M of b equal to 1? It's the permanent of this matrix, right? Without this part, because this is how we chose it. So this is permanent of this part of our matrix. And what is the permanent of M when b is 0? This is equal to sum over all permutations such that sigma I L is different JL for all L to SB, where so if we substitute instead of B0, the only permutations that are left are ones that do not go through B. So for every, so this is pi of I. Okay, so these are, and we want to compute the sum of these two things. And the sum will, so, okay. Can I give a better intuition? Yes. Now let's take the permanent of this matrix. What happens if there is some set here? So let's write it. In pi. This is couple. It doesn't matter. So we take any permutation here. There are permutations here that pass through some of these positions. Okay, we partition this set to two sets. There are ones that pass through some of these positions. In this case, the set T will be non-empty because the positions are coupled. So whenever we have a permutation that passes here somewhere, we have the permutations that pass through exactly the same positions here. But since there is a unique way to complete this to a cycle cover of this graph, we count such paths with multiplicity 1. I will write it formally. I'm just trying to. On the other hand, when we have something that does not touch anything here, there are two ways to complete it to a cycle cover. So these permutations will be counted with multiplicity 2. Okay, so I'll try to write it more formally. So, okay, every pi, this is a permutation of this big matrix can be written as a permutation of this matrix and the permutation of this matrix. Why this is so? Because these two things are 0. So when we take a permutation of all of this and we want to get some non-zero value, it's a permutation of this part and then a permutation of this part.
I thought the coupling required that there will be some non-zeros in the...
Yes, but so we imagine that they are coupled, but we can argue on the matrix we started with. So yeah, in the coupled matrix, there will be some non-zero entries here. But when we look on the, like when we assume that they are already coupled, we can look on the original matrix. Okay, if I'll try to explain, if it will not be clear, I will try to explain again. I'm not sure that I'm doing it in the best way possible. So we write it as sum instead of pi of sigma and tau. And we partition it to two sets. One is that for every L, sigma IL, so sum over sigma, so that for every L, sigma IL is different than JL. And here is sum over tau, something, plus sum over sigma, so that there exists some L, sigma IL, JL. And we took this sum and partitioned it into these two sums. Now, if for every L, this is the IL is different than JL, then the sum over tau is 2. We can push tau to the end, and it will give us exactly 2. On the other hand, when there exists some L that this equality holds, the cycle cover can be uniquely completed. So when we push tau to the end, this thing is exactly 1. So we feel, okay. And this is because of these two properties. I'm going to continue this here. Now, so remember, we want to compute the sum of these two permanents. So the permanent now this thing, this permanent, is exactly one of the two things written here. So here there is a factor of 2. It's exactly one of them. So we have sum over sigma, such that for every L, sigma IL is different than JL. Product I from I to S in sigma of I. This is what we wrote above. It's exactly what is written here, but we took only one of these. So we have another one of this. So we have sigma, sum over sigma, that for every L, sigma I of L is different than J of L. The same thing. And we have another sum, this sum over all L, that there exists an L such that sigma IL is equal to JL.
So what you wrote is not an equality for the top. You said permanent at 0 plus permanent as 1. then you don't have this thing twice.
Yes, so I want to,
You want to subtract.
no, so this is an equality,
Yeah, from there, but
and
not
this
from-
is an equality as well. I'll try to explain. So here we have sum over all permutations. So the matrix written up there is this matrix. So we have sum over all permutation, so this sum partition the permutation to two sets, the permutation sigma. Either there is, for every L, IL is not mapped to JL, or there exists some L that IL is mapped to JL. So I want to say that this overall is exactly the permanent when B is 1. Okay, so we somehow used this rosette graph to get different weights on the permutations in such a way that we actually got what we want. I'm not sure. So I'll say again what happened, at least. Since we coupled all positions, every position here with a position here, when we take the permanent of this matrix, there are some permutations that pass through some vertices, through some positions here, and then their weight is 1. And there are things that do not touch this set at all, and then their weight is 2. We take one of the two things with weight 2 and move it to the other side to be the complement of the things that pass here through somewhere. Yeah, so is it sort of clear? Or yes?
You're saying, think of X with these nodes as a set of edges that we're possibly adding to the graph. How does that change the permanent? Well, it changes it by, when we set those edges to 1, we add in to the set of matchings that existed before, the set of matchings that used these edges.
Use the new edges, yes.
Use the new edges.
Yes.
So, the matchings that don't use any of the new edges should count twice. The matchings that do use the new edges should count once.
Yes, exactly. Okay, so this is how you get, how to use the permanent to allow Boolean sum. And this matrix, we did not touch anything here. So we did not duplicate variables or add anything. So we just added some few rows that has some constants in them. Okay. So maybe the only thing is to okay, there is actually. We made one observation a few days ago that is sort of related. In some sense, it shows. Okay, there are two options. One is to show how these 3 steps, to show again how these 3 steps actually prove what we want. And this will take about, I don't know, 10 minutes. So do you want to see it again or no? Okay. So the other option is some observation that I think is correct. You can tell me if it's wrong, that we had. That in some sense show that perhaps it depends. Okay, I'll tell you and then you can tell me what you think.
You want to comment also which parts
Okay, so
what
maybe.
we believe now is
Yeah, so as I said last time, we started discussing these issues because we thought we tried to prove lower bounds for non-commutative circuits, which are a more restricted computation model. So non-commutative means that variables do not commute. And we try to understand if all of this works in the non-commutative world or not, if some version of the permanent is complete or not. And yeah, so there are three, as I said, there are 3 steps to the proof. So the second and third step only sort of use properties of, not of the variables, but only of the underlying field. So these 2 steps are also pretty simple, like the same thing. You need to pay attention, but it's the same thing.
What is the parameter?
The same polynomial.
What's the order of the polynomial?
The way it is written.
From left to right
X.
in the columns? Oh.
It's pretty different because you're not going by cycle cover, for example.
Yes, this is true. However, the cycle cover only applies to matrices with field elements. So the only way we actually used it is with matrices that had constants from the field in them. Again?
commute, yeah, it's a field.
Yeah, and the field elements always have all the structure. So you're right, you need to take care of it, but it's not. The first statement was actually, the way it was proved was by some inductive argument, which sort of is balancing circuits. This is how it was proved like 20 years ago, some time ago. And balancing circuits fail in the non-commutative world. So we know that we cannot balance circuits. This is something that Noam Nissan proved.
What do you mean by balance?
Yeah, so I'll state this is just
Given formula.
no formulas. I think will work. So okay, I'll write a formal statement and I'll try to explain. So what Noam Nissan proved, there exists a linear size non-commutative circuit C such that the depth, the circuit depth of the polynomial it computes is linear as well.
So the formula size is
Exponential. Yes. So Noam constructed some specific non-commutative circuit of linear size that you cannot make it be of shallow depth. We know that for in the commutative case, this is always, so just in reference, in commutative, the circuit depth in this case is at most O.
Well, you need the degree to be linear.
Yes, but I ignore
The
it.
degree is linear.
Yes, so there is a huge difference in balancing things, making them of commutative circle. Yeah, okay, this one.
So everywhere the degrees are
Yeah.
Yeah, it's a
there's
very
one
simple.
polynomial, C hat. The polynomial could be written like this. That's linear degree.
Yes. Yeah, in the commutative world, it has actually a very small formula, this polynomial.
Is it something like just alternating,
So,
adding adding a new variable circuit? Sorry, adding a new variable and then multiplying by a new variable.
it's this, I can write it. It's very simple. So let's C of 1, C of 0 will be 1. I'm defining this circuit C by induction. C of 0 will be 1, and C of I will be xi 0, C I minus 1, x0 I plus x1 I. No. It's just a name. So we take the previous circuit, one time multiplied it from both sides by x0, and in the other time multiplied by x1. And this has a linear depth. Any non-commutative circuit computing this has linear depth.
Is it even possible to balance formulas in the non-commutative case?
Yes, it is. Yeah, but the first step in the old proof was actually it was almost balancing a circuit. I don't have an explicit, it's not a formal statement. But as I mentioned in the previous talk, there is some new paper of Malod and Portier. They proved this statement by the proof that we saw in the last time. And this proof...
Via multiplicatively disjoint circuits.
Yes. Yeah, they use something they called multiplicatively disjoint circuits. And their proof almost works as it is. You need to take care of one more detail, sort of. But it's their idea is pretty much all the details you need. This is about the non-commutative world.
So that was in writing a circuit as a sum of formulas?
Yeah, this is the first part of the, there are 3 steps.
Right, I'm just trying to remember what the order of the steps was.
This is the Cook-Levin, yes.
Yeah.
So the conclusion is that the permanent is complete in the
Yes. The permanent in this order.
in what?
In this specific order is complete. And we also try to think about a different model, which is a non-associative world. What is a non-associative world? So it is commutative. This is non-commutative. This is non-associative. In a non-associative world, every monomial has a specific way of creating it. We specify the way we multiply other things in order to create it. And so in a non-associative world, so let's switch color. So red will be non-associative. This step is actually the same thing. It's not different. And it turns out that actually proving universality is not I don't know, very simple. And one way, I'll try to explain why this is true. So in the non-commutative world, we need to define the permanent where this monomial has a specific way of creating it. So we need to fix some way. And in this part, when we had a product, we used that the structure of these monomials. So when we had a product, it was we sort of assumed that the monomials of the permanent are partitioned according to this order and then to this order inductively. But we do not know which of the orders is the correct one. Like this was S1 and this was S2. In general, it's not equal. It could be unbalanced to one side or to the other side. So to
when we get an arbitrary non-associative formula, we
yes.
The partition may not work automatically with the ordering we define of the permanent.
Yes. So to overcome this, you need to define. So there is the following question. Given n, what is size of 3 u? U is for universal, so that every other tree of size at most n can be put into the big tree U. And what does this operation win? We have this, so let's think about binary trees.
It's a minor.
Yeah, this is a minor. A minor means that we can delete some edges and we can collapse edges. So if we have a long path, we can make it just one edge. We have these two operations, and it turns out that to handle this question, this is the type of question.
Combinatorial essence.
Yes. And I'm not so. Yeah, we actually didn't really check it, and and we don't know if this is known or not, this specific question, but this type of questions were studied before. And it turns out that, as far as we know, this size is something like, I don't know, n to the 5, something pretty small.
What do you mean as far as you know?
No,
We think that we can prove it. We didn't check all the details. So the size of U. So there is a polynomial size circuit tree, that can embed all the exponential it depends if it's order or not, but all the super polynomially many trees in it. Maybe another thing to note is when we do not allow collapsing of edges, we just take this operation out.
So we just ask that T would be a subgraph of an induced subgraph
when we require T to be subgraph, then this question was asked, and the answer is n to the log n.
Yeah.
Upper and lower.
Yes, it's like, it's very tight here. What is
So
it
the-
like?
So like the upper bound is fairly easy.
Yeah.
Something like, so a universal tree of size n, on the left, a universal tree of size n over 2, and on the right, a universal tree of size n over n minus 1.
Yeah, exactly.
Yes. Yes, so
The
what,
lower bound is not so simple, but
yes. Yeah, what Russell said is that u of n, the size of un is at most u of n minus 1 plus u of n over 2. So maybe,
Plus 1 or something.
yeah, there is some maybe. But why is this true? We take a tree of size n. One of its parts has at most n over 2. We put it here. The other part has at most n minus 1, and we put it here. So we have this recursion, which is this quantity.
You can just unravel the biggest term and until you get about n over 2 terms of size u of n over 2.
Mm-hmm.
It gives you log n factors of n.
What else? The lower bound is not complicated, but it's clever. I'm not sure. Yes. Okay, so this is related to the non-associative question.
and maybe it's worth saying that in the
Ah.
subgraph question, if you ask not for a tree that contains all trees as subgraphs, but you ask for a graph that contains all bounded degree trees as subgraphs, then you can do it. That's a result of Friedman's contingent.
Well,
There's a big group there's a graph polynomial.
Depends whether-
Yeah, I just
Depends
wrote it to be.
yeah, you count, okay, whether you count edge-induced subgraphs or node-induced subgraphs.
Edge-induced subgraphs. Edge-induced
Yeah.
subgraphs, then you can do it with linear size.
And this is an
The
expander.
linear number,
Of edges and vertices. Yeah, there's a bounded degree graph. In fact, any sufficiently good expander
yeah,
contains all trees as or bounded degree trees as subgraphs.
right. But then, so for node-induced
It's
subgraphs,
quadratic.
it's, this is
The Nogalon and the
okay, but, so the first paper was Kanan, Rudish, the implicit
implicit
representation.
representation. Yeah, these are much better bounds. You're right. That's for the implicit your paper. But I think there are better bounds. There are tight bounds. But I think that Capalbo and Alon and Capalbo is the last word.
Okay. So I'll have one more observation is that there exists f for every
Same thing should be true about B. But you can have there exists an F in B. With the same.
No, this is f in n variables. And degree b. So
I'm just saying that the same
Okay.
argument, like we discussed it yesterday in that cafe.
yes.
So the same thing is true about BP as opposed to BNP. like everything which has circuit size n to the d
Yes,
is in D
okay.
by definition. So you
Yeah,
just have
okay.
to show that there is a polynomial of circuit size n to the d which requires circuits bigger than n to the d over 2 or something like that.
Okay. What I'm trying to point, there is some result of Cannon and some other, Cannon by himself, that sigma 2 contains arbitrary hard functions. So there exists a function in sigma 2.
So for every C there exists.
Yes. For every C there exists with Boolean circuit complexity n to the C. And we don't know how to prove this for NP, for example. At least I, yes. And here we have there exists and for all in this statement. We have two quantifiers. And what I was trying to point here, that in a circuit world, in an arithmetic circuit world, you can sort of remove one quantifier. VNP has only one quantifier in it.
Yeah, but it's counting one.
Yes. So, yeah, this is.
It's true, we could replace that sigma 2 with one counting quantifier. Yeah.
Yes. Which is, so like, yes?
I don't know something. Doesn't this separate VNP from VP? Like, because maybe...
No, even
No.
for P versus NP, there may be a problem in NP of complexity linear that requires, if P equals NP, it's possible that these problems in NP that can be solved
Like
in linear
It's
size non-deterministic circuit requires size n to the 10.
But
Wait,
in
what
fact,
is it then?
it follows from this
N
that
to
if
the D?
n to the d, yeah.
And the degree can be linear or something.
The degree is also d.
The degree is D, yes.
No, but we usually consider like functions of non-constant degree.
Right.
Yes.
And there may not be a nice way of interpolating them into a single function.
Oh, because for every D and it's like a different
Different function.
Yes.
This
Right.
is like the...
Yeah,
okay.
Yes.
and the upper bound for VNP might be, it will also probably be like n to the d. You write them as the sum of things,
Yeah, but
the number of things you're summing up, and the complexity of the thing you're summing
yes.
probably also grows with d.
Okay, so yeah, the only what I was trying to say here maybe is that maybe VNP is not the correct meaning of explicit in some sense, like anything that does not prove a lower bound for the permanent maybe is not explicit or something like this. I don't know.
But the permanent meets all of our definition of explicit, right?
Yes.
So, what this completeness result says was, as long as we get sufficiently large lower bounds, then it's okay to use this as the model of explicit, because we'll get the same lower bound for permanent.
So, yeah, the power of VNP here comes from there is a sum and there is a Boolean something here. And here there is just monomial. Right? This is like the structure of VNP. This is a very simple thing, and the size of this Boolean this Boolean algebra hides inside the definition of VNP. Like, so
I believe this is slightly like misleading. Like the power where VNP takes its power is not the Boolean sum, but it's the non-uniformity. The same thing the same observation applies to VP, and there you have no Booleans. The important thing is that the classes are non-uniform. That's what allows you to do this thing. Like instead of this Boolean sum, it could be just sum of monomials, and
okay.
Yeah, you are saying that it's very similar to the result in Boolean search complexity, that there are functions that require n to the c, but cannot be done in n to the c minus 1.
it's the same thing.
Yes.
And
Yes.
like the issue here is the non-uniformity.
Yeah, that's it.
Okay. Yes, maybe you're right.
Well, could you prove the same thing for uniform VNP?
No. Yeah, this will be very interesting. Yeah, so, maybe a different way to state the same thing is that any argument better than the counting argument in some slight way is good, like we'll say something meaningful. Maybe this is the way to think about what I
So just make sure that the innermost function is, so that the is uniformly computable. So just say that so there's an underlying formula, right?
Yeah.
So just make that formula have to be computable in polynomial time.
Yeah, this part.
Equivalently, you can have a Turing machine computing the coefficients of your polynomials for all n. Yeah. So you
Well,
want
so then,
no, I understand. This is two equivalent things. What you're saying is that there is a G, there is a formula in the definition of VNP.
Yeah.
Make a Turing machine compute all these formulas. Another thing which is equivalent is that we have a sequence of polynomials, one for every n, that is in uniform VNP. It is in uniform VNP for all these multivariate polynomials. There is a single Turing machine computing the coefficients of all of them. When you give the name of the coefficient, it gives you the coefficient.
is that really, is it
What?
really the same? How?
It's only if you had
It
your
could be
formula,
Boolean.
the Boolean.
This part could be Boolean. Like, it would be interesting.
No, so what's the Boolean formula?
So you can assume that G has two parts, has Boolean in E, and then like a monomial. It's a product of X plus EI, like something of this form. It has two parts. One is Boolean, and the other is a very simple arithmetic formula. Thank you for your